Good afternoon.
Good afternoon.
You guys sound about as excited as I am to be here today. All right. So did anybody do anything amazing over the weekend? Nothing amazing?
Our baseball team went down to a tournament and we won it.
You won the tournament?
Yep.
That's pretty amazing.
Yep.
Where was it at?
Chandler Prep.
Awesome. So how many schools were there?
A lot.
Yeah? You guys won the whole thing?
Yeah.
That's pretty sweet. That's awesome. Good job. All right, well, let's see. Is everyone there at Mogion?
Yes.
Yeah.
How about at Hopi?
I think they're still coming to class.
All right.
Yeah.
Do I need to send out an email to let the principal know what time this class starts? Yeah? Yeah. All right, how about Alceste?
Cesario should be coming, I think.
Okay. Well, I'm going to mark him absent, and then you tell me, or have him tell me if he comes.
Okay.
Anybody else?
Everybody else is here.
Okay, awesome. Thank you. All right, and let me know if everybody didn't show up in Hopi too. All right, well, today we are going to work on section 9.3. Which is on the hyperbola. And then, so we'll probably finish it today. Okay. So, anyone have any questions, comments, concerns before we get going today? All right. Well, let's get going here. So 9.3, the hyperbola. So we're going to talk about the standard form of the hyperbola. It's going to seem very similar to what we've done with the ellipse, with the parabola, and then even back with the circle. Okay, and then at the end of class, then we'll talk about guidance systems or an application of the hyperbola. All right, so the hyperbola is the third type of conic that we've discussed, fourth overall, with circle, ellipse, parabola, and now the hyperbola. The big difference, so to speak, between the hyperbola and the ellipse is while the ellipse is the set of all points that's the sum of the differences of the distances to the foci, the hyperbola is the set of all points where the distance, the difference between the distances is constant. So let me show you a picture here. So here we have the two foci. With the ellipse, it's the set of the points that are the sum of the two distances. With the hyperbola, it's you take any arbitrary point on the hyperbola and measure the distances to the foci. And it's the difference between these distances that's the same. Okay, so that's a little different. Now, we still have our vertices, and we still have a center. We have each part is called a branch of the hyperbola. And it looks like two parabolas back to back. All right, let's see. Okay, the standard form of the hyperbola. Okay, so this screen looks an awful lot like the one with the ellipse, but I'm going to go through it again. So the standard form of the hyperbola with center HK is So we have x minus h squared over a squared minus y minus k squared over b squared equals 1. So this is almost identical to the standard form of the ellipse. The difference being that instead of a plus in the middle, there's a minus. So that one change changes the graph considerably. The other standard form is y minus k squared over a squared minus x minus h squared over b squared equals 1. Now notice that when you're determining the center hk, the h goes with the x always, the k goes with the y. Now, with the ellipse, what determines a horizontal or vertical ellipse is which of these numbers in the bottom are bigger. With the hyperbola, what determines which one is bigger is if the x squared is bigger, then the hyperbola opens left and right. If the y squared is bigger, then it's going to open up and down. Okay?
They're all coming in now.
Okay, thank you. Thank you.
Mr. Strong, Cesario's here now.
Okay, thank you. Appreciate that. Okay, so which one comes first? The x squared or the y squared determines the orientation of the hyperbola. All right, now, to find the foci, the distance to the foci is still c, but the equation to find the foci is c squared equals a squared plus b squared. So if that looks like the Pythagorean theorem, it does. It's the same formula. Okay, so that's a good way to remember it. Now, when the center of the hyperbola, which is at 0, 0, and most of the ones that we do will be, then these two equations simplify to these two. So the h and the k go to 0. So if the x squared comes first, the hyperbola opens left and right. If the y squared opens first, it opens up and down. All right, anybody need more time on this page?
Yeah, could you give us some more time, please?
Sure.
Okay, we're done.
All right. Okay, now, so just to kind of show you the difference between the hyperbola and the ellipse equation that we did last, is that with the ellipse, it has a plus in the middle here, whereas the hyperbola, it's minus. And then to find the foci with the ellipse, it was c squared equals a squared minus b squared, whereas with the hyperbola, it's c squared equals a squared plus b squared. So those two sign changes, they change a lot when it comes to the graph. All right. So when the x is first, when it's x squared minus y squared, the hyperbola opens left and right, or horizontally. When the y squared is first, then it opens up and down, or vertically. Okay. So the way that we actually graph it, we use this this box in the middle to help us. So let me explain where this comes from. All right, so first of all, once we identify the center is 0, 0, then just like the ellipse, we use the numbers underneath to tell us how far to go over left and right and up and down. So the square root of 4 is 2, so we go left and right 2, and we draw our little points there. Square root of 16 is 4, so we go up and down 4. And then now if we were doing an ellipse, then see we would take and combine, make our ellipse using those 4 points. But it's not an ellipse. So what we do is we make a box containing those 4 points, a rectangle. And then we draw the diagonals of the box. Okay? And these are going to be what we call the asymptotes of the hyperbola. Now, all the box and the asymptotes, when I draw those, I draw them with a dotted line because they're not the hyperbola. But it's most of the work to get the hyperbola. So what we do is from the vertices, because the x squared came first, so we know it opens left and right. From those vertices, we go up and down, approaching these asymptotes. So we approach the asymptote above and below, and that gives us the basic look. Okay? All right, so see if you can do that with practice 1A. All right, so your hyperbola should look like this. Okay, so again, the center is at 0, 0. In the x direction, you go left and right 3. In the y direction, well, there's a little invisible 1 right there, so the square root of 1 is 1. So you go up and down 1. You make your box. Then draw the diagonals of the box, the asymptotes. And then since the x squared is first, then you draw your hyperbola to open left and right. If the y squared was first, then we would make it up and down. All right? Any questions? All right? All right, now, next to find the asymptotes of the hyperbola. Okay, I like to use this equation right here. The y minus k equals plus or minus b divided by a times x minus h. So this sort of combines these two. Some books have these quite a bit differently. So I'm going to try to kind of demystify the asymptotes to find them. Because frankly, let's say if you were to Google it online or whatever, or ask for some different help, different books have kind of a confusing way to do this, to do the asymptotes. So if you've got that written down, let's just go through it here. All right. So let's say we want to find the asymptotes, the equation of the asymptotes. So those that's like the diagonals there that help us find the hyperbola. So we start off with the y minus 1 here. So y minus whatever. So y minus 1 goes here. The x minus 2 goes here. You don't put the exponents on either one of them. And then it's plus or minus, and then whatever number's underneath the y, the square root of that, 2, over whatever number's underneath the x, the square root of that. Okay? And that's it. So that's the equation for both asymptotes. Okay? So see if you can do practice 1b. All right, Cesario, what do you have?
Would it be y equals 1 over 3x?
Okay, except just put plus or minus in front of the 1/3, because there's actually two of them.
All right.
Okay, so one's going to go this way, the other's going to go that way. They make it like an X. So plus or minus. Okay? Any questions on that? All right, good. All right, so as I mentioned before, the formula to find the foci of the hyperbola is c squared equals a squared plus b squared. So like the Pythagorean theorem, but not. Okay, so let's say that I want to find the foci for this. So I say, here's my formula. C squared equals a squared plus b squared. So c squared equals, so the a squared and the b squared are just these numbers down here. So they're already squared. You don't have to square them again. So you just add those up, and that's c squared. So then c is plus or minus the square root of 29 here. Okay? Now, here it's important that you know which way to add the c. If the hyperbola opens up and down, then you're going to add and subtract to the y value of the center point. If the hyperbola opens left and right, then you're going to add and subtract from the x value of the center. So here the center is 2, 1. Okay? So since they open sideways, you're going to add and subtract from the x value. So if the center is 2, 1, then the foci are 2 plus or minus the square root of 29, comma 1. All right, any questions on that? Okay, so for practice 1C, you don't have to graph that. I just want you to find the foci. So for practice 1C, just find the foci. All right, so Dwayne, when you got it, just the foci.
Plus or minus square root of 34.
Okay, and so that's the C. Okay, so C is plus or minus the square root of 34. So then what? And this is the center is at 0, 2. So then what are the actual coordinates of the foci? The plus or minus the square root of 34. You're going to add that to the x value or the y value?
X.
The x, because again the hyperbola opens left and right. So the foci then would be plus or minus the square root of 34, comma 2. All right. Any questions? Okay, before graphing a hyperbola, it should first be in standard form. Okay, we've actually had that phrase in every one of the conic sections. You need to have it in standard form before you start graphing. All right, so when we look at this one, see, why is this not in standard form? Well, because you don't have a 1 over here. You have to have a 1. So the easiest fix is just divide everything by 16, because 16 divided by 16 is 1. Now, in the meantime, the 4 will cancel with the 16, leaving you with x squared over 4 minus y squared over 16 equals 1. So that would be the standard form. Okay? All right, so then now you're ready to graph it. And so then you'd say, okay, the center's at 0, 0. You go left and right 2, up and down 4, make your box, draw the diagonals of the box, and then again, since the x squared comes first, then it opens to the side. All right. So go ahead and try practice 1D. All right, Emily, when you've got it in standard form, let us know what you get.
Y squared over 9 minus x squared over 4 equals 1.
2. That is correct. All right, any questions on that? All right, go ahead and sketch it out if you haven't yet. Just make sure that we're getting these right. All right. So let's just kind of show this one. So this one's a little different because the y squared comes first, so it's going to open up and down. So the center is still at 0, 0. In the y direction, you go up and down 3. In the x direction, you go left and right 2. You make your box, the diagonals of the box, and then you make it go up and down because the y squared is first. All right. So how many of you had that graph right? All right. Excellent. Excellent. So how many of you know what's the highest grossing movie of 2015? I bet if you think about it, you probably could figure it out.
Avengers.
Nope. Okay, let me give you another hint. It actually was the highest grossing movie of 2015 before it showed its first showing, because it was all from internet sales. People pre-bought their tickets to make it the highest grossing movie of the year before there was even one showing. Any guesses? Star Wars Episode 7.
Star Wars.
Force Awakens. All right. Now, the reason why I mentioned that, okay, now you mentioned the Avengers. The new Avengers movie outsold Star Wars in internet sales in 6 minutes. In 6 minutes. Anyway, so there's going to be a lot of full theaters, I think, for that movie. So 6 minutes. All right. So now let's do our little matching game. Okay. So the way we played before, here's our 3 equations and our 3 graphs, and we want to match them. Okay. So let's start with Emily. So you can pick any equation you want and then tell us which graph matches it.
C goes with 3.
Which goes with 3?
C.
C. So you're saying C goes with 3, like this. And that is correct, because here the y squared comes before the x squared, so this one opens up and down. So that's the easiest one to do. So great job. All right, now let's give somebody else a chance. All right, Rhett.
A goes to 2.
A goes to 2, all right? Let's see if you're right. So x squared minus y squared, so it opens left and right. And the center is at 0, 0. So boom, all right? So let's see if the last one checks out. If B goes with 1. So here the center is at 1, 2. Well, that's the only one that has the center at 1, 2. So that's it. And it opens left and right. So good job. Any questions on any of those? All right. All right, so when drawing a hyperbola, remember to first draw the box and the asymptotes, okay, the diagonals of the box. If you try to freehand it, just based on experience, your graph will not look right. It'll look goofy. So just do the box, but you want to make those when you draw them in, use dotted lines because they're technically not part of the actual asymptote. I mean, of the actual hyperbola. All right. So the hardest thing as far as graphing and putting them in a standard form with circles, ellipses, parabolas, hyperbolas is completing the square. Okay, so I'm going to do another one, even though we've done this already, just to have the practice with completing the square. Because, see, we have this extra x term. So what we do is we're going to combine the x terms together and the y terms if there's more than one. And then any constants, you just move those to the other side. All right, now, where we have a number in front of the squared term, we need to factor that out. So we're going to factor out a 4. We really don't have to worry about the y's. This is already a perfect square. All right, so now what number are we going to add inside the parentheses here to make this a perfect square? Anybody? If you know it, just say. What number are we going to add?
1.
1. Because half the middle term is 1. 1 squared is 1. So I'm going to add a 1 here. But I really, because I factored out a 4, I really added a 4. So I have to add a 4 over here to compensate. All right. Now, this is a perfect square. This is x plus 1 squared. All right. Now, we're good, except this needs to be a 1 over here, like in the last example. So here we're going to divide by negative 12 to make this 1. So divide everything through by negative 12. So now we get 4 divided by negative 12 is negative 3. So I put in the negative in front and then the 3. Negative 3 divided by negative 12 is plus 4. And then negative 12 divided by negative 12 is 1. But now, when we put it into standard form, see, because now this term is negative, so we need to put the y squared over 4 first. So it's y squared over 4 minus x plus 1 squared over 3 equals 1. So this one is tricky for a lot of reasons. Because some students, when you see this from the very beginning, and then you'll say, it'll like a multiple choice question on a quiz or a test, it may say, okay, which of these graphs is it? And so some students will be lazy and not put it in standard form, and they'll just say, oh, it's x squared minus y squared, so it's got to open left and right. Wrong. Because once we put it into standard form, see, it's the y squared minus the x squared. So this hyperbola is going to open up and down. Okay? So that's an easy miss there. Okay? The other thing that's a little tricky here is, okay, so remember the center is HK, and the H goes with the X. So the center of this would be -1, 0, not 0, -1. So that's a second common mistake that students would make, is identifying or misidentifying the center. Then once you get the center, see, in the y direction you'd go up and down 2. In the x direction you'd go left and right. How much? How much would you go to the left and to the right for making your box?
One and a half.
Just about. So the square root of 3, not half of 3, but the square root of 3. So it's about 1.7. Okay. So we haven't really, most of the time, our numbers under here have been perfect squares. And like, okay, the square root of 4 is 2, so we know we go up and down 2. If it's not a perfect square, you still take the square root of it. And so that's a little tricky there as well. Okay? All right. Well, let's have you do practice 1E. So just let's just have you put it into standard form. Well, we'll not worry about graphing it. Just put it in standard form. All right, so Jada, when you've got the standard form, let us know.
Is it x squared over 4 minus y minus 1 squared over 9 equals 1?
I think that's what you said right there. Good job. Any questions on that? Anybody like me to go through it? Okay. Okay, so you can determine the center of a hyperbola from its vertices by using the midpoint formula. So the center is exactly halfway between the vertices or the foci. It's actually the midpoint of the foci as well. So if you know one or the other of those sets, then you can find the center. Okay? So the midpoint formula, this is just from Algebra 1. You take the average of the x's and the average of the two y values. So let's say that these are my vertices, 3, -5, and 3, 1. And I want to find the center. Well, the average of the x coordinates is 3. The average of the y's, well, -5 plus 1 is -4, divided by 2 is -2. So then the center is at 3, -2. All right, now that's really the main focus of this example, no pun intended. But what I want is to, I want someone to tell me, how is it that I know just based on these two vertices? How do I know that the y comes first and not the x? How do I know that?
Because you can tell, like, if the like the vertices are like horizontal or vertical, and that'll tell you if it goes up or down or left or right.
Beautiful answer. Beautiful answer. So here the vertices are vertical, so that means your hyperbola is going to open vertically. Okay, good job. All right, so on practice 1F, wait, I think this should be 1F. Just all I want you to do is find the center. So you don't need the asymptote. So we just want to find the center. All right, Timmy, what do you have?
The center is 6'2".
6'2". And is this hyperbola going to open horizontally or vertically?
Horizontally.
Yep, very good. Any questions? All right. So an application of hyperbolas. It's interesting. I didn't even know this application till I'd been teaching for about 15 years. A real life application which hyperbolas are used is in long range navigation. Okay. Mostly in the military. Okay. Now, in the military, they call this LORAN for long range navigation. Now, so basically what this is it's a way that ships at sea could navigate through troubled waters or minefields or, coral reefs, fog, whatever, just using their instruments. Okay? And so I'm going to explain this to you. Now, I had actually seen this also, this method of navigation used in a sci-fi movie. And I was like, I didn't understand that at the time that they were actually using the same method of navigation using hyperbolas. Okay? Because they were talking about coming on a hyperbolic trajectory, and I thought it just sounded like science fiction-y. Okay? But they're actually using the correct math. So this is kind of how it works. So suppose that this is a ship at sea. And so what it is, so LORAN, that's the long range navigation. So what the ship does is it sends out a pulse. And then when this method was first, when it was first initiated, the pulse back would be a sound. Okay? And then later it was upgraded to be like a laser device. Okay? But what the ship would do is there would be 2 receiver stations. And so all up and down the coastline of the United States, they would have these receiver stations. And so if a ship was, 20 miles out or whatever, they would send this signal. And so these receiver stations would respond. Okay, but they would respond differently depending on how far away they are. Okay, so one would respond, the second would respond, and so then what they would do is measure the difference between the response times. Okay, now if that sort of sounds like a hyperbola, it is, because remember, the hyperbola is the difference between these distances. Okay, so here's the receiver stations. So in the problem on your sheet, it says, suppose these receiver stations are 100 miles apart. So what we'll do is we'll say that, okay, that right between them is at 0, 0. And so we'll put one at 50, 0, and the other at negative 50, 0. Okay? So then what we're going to do is then say, we send out the pulse, and it says that, let's say the difference. So now we've upgraded their equipment. So we're not using sound anymore, but we're using radar. I mean, not radar, we're using lasers. Okay? And so the one laser signal comes back, the other laser signal comes back, and the computer measures the difference in the time to be 0.000108 seconds. Okay, so a human couldn't even measure that distance, that difference. But this computer can. So then what it does is it adjusts the speed and the course of the ship so that the difference, as it sends out more pulses, it maintains this difference to always be the same. And so what it does is it sends the boat in on this hyperbolic trajectory. And so what it is they've got this trajectory worked out so that it will miss all of the mines in the harbor or all the coral reef or whatever. It will be a safe path into the harbor. And so the boat will follow that path in. And so then it keeps sending out these signals. All right? Then we can also determine how far the ship has to go to the beach, or how far off it's going to be from the center, this hyperbolic path. And basically, you know that the rate of light is 186,000 miles per second. So then if we multiply rate times time, we get the distance is 20.088. That's the difference between these two distances. And so the difference between the two if we were to divide that by 2, then it would basically tell us from the center, where's the vertex here? Where's the vertice? How far would we go to the right? And so because this distance is like the major axis between the hyperbola. So by dividing by 2, it tells us how far we are from exactly the middle between those two stations. So that distance then would be 10.044 miles. So we know exactly where in the port we're going to be, okay, where we're going to land, just based on these signals, okay? And so the ship can navigate completely on instruments. It doesn't even have to see the path or whatever, okay? And so the U.S. was the first to develop this type of navigation using hyperbolas. And so it gave them us an extreme advantage in the early 20th century as far as our boats being able to navigate and our shorelines being protected. So anyway. All right. Well, so I thought that's kind of an interesting application. All right. So the last thing that actually ends the part on hyperbolas. Okay. The last part on this sheet, though, is you might remember from the very first day that when we started conic sections. Okay. We were talking about classifying conics from their equation. And so I had you write this down. And so I've got it again here. So it's what you do is you're mainly comparing the A and the C, the two coefficients of the squared terms. So if A equals C, then you have a circle. If A times C equals 0, then that means one of these doesn't exist. One of the square terms doesn't exist. And if you only have one square term, it's a parabola. And then if their product is positive, meaning they're both positive or both negative, you get an ellipse. And then if their product is negative, so one's positive and one's negative, then you get a hyperbola. All right, so then what we would do is to look at these. So you'd say, okay, there's only one square term. That's a parabola. Okay. There's two square terms. One's positive, one's negative. That's a hyperbola. Okay. There's two square terms. Their product is positive. So that's an ellipse. Two square terms that are equal. That's a circle. Okay. So we're on our last minute here. So I do want you to write down the conics for practice 3A. It'll just take you a minute to do all of those. And then we'll start tomorrow's class going over those. And then we'll probably do all of 9.4 and maybe even some of 9.5. Okay. So you want to have both of those probably printed out before class tomorrow. Okay. Questions? All right. Well, sayonara.